Good.
I think I'm online.
Can you disconnect now, Dino? Yeah.
Yeah, thanks for doing all the work,
Oh, yeah,
basically,
no
for
problem.
this meeting.
Yeah, perfect.
Okay, so yeah, you do the slides then, and
Looks
I'll
like they should
do the
start up any second now.
talking for the status part.
Yeah.
I guess as usual.
I'd say start up.
Yeah, yeah, and yeah, you'll do the take the
Little
notes.
starters
Yeah,
and-
yeah.
Yeah, I'll just do them.
Yeah. Okay. Yeah. Hi, everyone. Welcome to PIM in Yokohama. Yeah, we'll start with some agenda bashing and status update. So you should all wear a mask, by the way, unless you are actively eating or drinking.
I don't think your sound came in the back.
Just go closer to the mic.
Okay. All right. So this is the note bell. Hopefully, you all seen this. It's how we work in the IETF, and yeah, things you should be aware of to participate. Okay. This is our agenda. It's a very full agenda this time. Much fuller than usual. So I'll just move on quickly unless there's any comments here. All right. So let's look at the working group status. So yeah, we have some drafts about PIM-DR election that have been sitting around for a long time. We need to try to make progress on those, but we'll have a presentation today for one of those drafts. Otherwise, there's actually some RFCs that have been published or approved. So let's see. So registered packing and assert packing, they have both been approved for publication now. On the slide here, it says revised draft needed on assert packing, but that was like until the status until today, I think. It's actually approved now. So yeah, so assert packing, registered packing are both approved for publication. We also have IGMP MLD proxy Yang that is in the RFC editor's queue. Then we have 3 documents that are like BIS documents for IGMP and MLD. Most of you hopefully remember we've been working on moving IGMP version 3 and MLD version 2 to internet standard or full standard. So those 3 documents all have to do with that. One is IGMP version 3 BIS, one is MLD version 2 BIS, and then there's like an IANA considerations that also been updated. Okay, next slide. Okay, we have some point to multi-point drafts that are not presented this time. PIM Lite will be discussed today. There's Lisp extensions draft has been sitting around for a while. So that's not discussed today either. So I guess that will probably go to working group last call soon. There's a MOFR draft will be presented today. Also further down here, we got lessons learned. There was just an adoption call that finished a few days ago, and yeah, Mike is a co-author on that. But yeah, I believe that it passed the adoption call, so we'll make it a working group document. There were some comments about allowing more people to contribute and having more details about the history and so on, and yeah, everyone should be welcome to contribute to the draft if they wish. So it would be great if anyone or you want to contribute. There's also this it is 736 biz that working group last call just ended. There were no responses though, but so I'll leave that to Mike since I'm a co-author. But yeah, Torlis.
Unless I'm mixing up the numbers, that's the bits in the header, right?
Yeah.
Yeah. No, I did reply that I would love to see an example of how to write this up, which I think we've done in the 2 drafts that passed the last call, but as an example, how to write that stuff. And then this trick that Alvaro mentioned, that putting in explicit bits is not an actual allocation, but should be understood as an example to how IANA might represent it, because I was sitting there writing my assert packing and was really wondering how would I do a nice picture without, being sure that IANA is going to allocate these bits. So these 2 descriptive things would be really nice improvements.
Okay, great, thanks. Yeah, that's what we had for the status. Yeah.
So Human, the one draft that we don't have an update on this IETF is the P2MP policy ping. And you sent an email to us and the MPLS working group asking for an early allocation. And so we said, yeah, sure, it sounds good. It meets all the requirements. They said the same thing. And the ADs were included, including Alvaro. And then at the same time, Lois said, okay, you need to start the process over again and request it. So it sounds like if Loa's right, we need to, after this IETF, we need to resend a new email, just copying what you requested to the ADs, copying the MPLS chairs. They'll say, yes, we approve as well. And then I guess it should be okay. Does that make sense?
Yeah, I think that makes sense. Yeah,
Oh.
I was going to ask about that actually. Thank
Yeah.
you.
Okay. Okay.
So I guess we should start on PIM Lite.
Yeah, how do I get out of here? Oh, here we go. Yeah, PIM Lite.
Human, we'll start with a PIM Lite.
Okay. Can you guys hear me actually?
Turn it on. Can you turn it on? Is it on?
It is on. I got the thumbs up.
Oh, okay.
Play here.
I can be louder. Yeah, so just a little bit of update on the PIM Lite, and I guess you kind of need more input to take it to the next step. You can go to the next slide, please. So obviously with the PIM Lite, what we said is that there is no hello messages. There is as such, because there is no hello messages, that means that when it comes to a LAN type of environment, you're not going to be able to detect the replication, and there's no asserts, or you're not going to be able to stop duplicated traffic coming from the source, that type of a LAN environment. So I guess I need to add something. Mike brought it up too, actually. I need to add a paragraph that kind of says that this protocol, what do you want to call it, this method is only good for point-to-point type of environment, or in a tunneling mode when you want to go over here or something like that. So I will add that. With the same token, when it comes to the rendezvous points, EDR, all these other pieces of the multicast in the SN world, they all need to be sitting in the actual PIM domain. There cannot be a RP that is on the other side of the PIM light domain. Again, all of this stuff is because this PIM light is only going to support the PIM message type 3, which is the join and root. So we did bring up on the draft, what are the type of interfaces of PIM light. From the failure point of view, again, there is no hello. So you need to use some other type of protocols, including, as an example, BFP. If anybody thinks about anything else, by all means, bring it into the working group. We will try to add it. One more thing that was brought up by Mike, good point, is that when it comes to the security of the PIM light interface, what we need to do. As of now, just me going through some of the drafts that were out there. Authentication is the first thing that comes in my mind. Like IPsec authentication, I'm not 100% sure if PIM supports like a SHA-256 or HMAC type of authentication on the interface. But these are the type of things that I'm thinking right now to add to this draft. I know there's a draft 59 something that was for security of PIM. I was kind of going through that. I didn't see anything that kind of caught my eyes. They were all talking about different type of messages, but the join and the prune and how you should interact with these other PIM messages from security point of view. So that didn't catch my eyes. But I'll look a little bit farther. And last but not least, when it became part of the RFC 6559, I did go through that RFC. There is a bunch of lines and paragraphs with regard to how the TCP needs to be negotiated over the hello messages. Obviously, this draft invite doesn't support hello messages, so I couldn't see that there is anything that I can bring into the draft. That said, if it becomes to a TCP point of view, I guess there needs to be a configuration. So I think at the end, what we decided with TCP is maybe with an informational draft that kind of explains when it comes to TCP and this PIM light, how we can configure the TCP under the PIM interface, PIM light interface, and take it from there. I couldn't think of anything to bring in from TCP point of view. Again, feel free to go to the working group and correct me if I'm wrong.
There aren't two questions. Do you want to take them now or comment? Yeah, sure.
Could simply be, an update for 6559 is saying that you don't need the hellos when, the interface is configured. I mean, don't do unnecessarily many drafts if they just tend to be one page long, right? Just to, yeah. Yeah. Yeah.
I was going through it and I see most of the draft was about just how the hello is negotiated.
Right.
The only thing I could see is that, yeah, you're right. There's a sentence in there that says, if you want to use TCP, then there needs to be configuration under the PIM light. Is that sufficient in your opinion?
Well, I think the question is, how do you figure out when you open the TCP connection that it is for PIM light versus PIM, right? So can you figure that out from the port number? How do you do that without the PIM hello? I think that's a question. Address, port number, right? Whatever you choose, so that this is a TCP socket for PIM light mode, PIM TCP. Yeah, the other stuff with 6559 is that it's only experimental right now. So if we want to have this being standard, then we have a down ref, and I think that's an area director question in terms of how much pain that's going to cost us.
Yeah, Alvaro.
Alvaro Thana, FutureWay, not answering Torles's question. You said something in the last slide about this on a LAN interface and how it's not going to work too well, and so you're going to recommend only using it on point-to-point?
Yeah, I think.
So the question is, are you recommending only putting it on point-to-point, or just going to say this only works on point-to-point, period?
going to the broadcast the type of thing that gets there to enterprise.
No, I understand. So the question is, in the draft, you're going to say this is only applicable to point-to-point. That's it. Okay, good.
This is Dino. Regarding the TCP interaction, was it your intention to only run over TCP or have either UDP or TCP?
No, I just think it's like open.
Uh-huh.
But there was a comment that was saying that, what is the interaction with 7559, which I was looking at the last update.
Okay. What I was going to suggest is, as part of your procedures, rather than add more text, just send a SYN message to the port that's allocated. And if you get a reset, then fall back to UDP and be done with the issue.
Okay, now this is better. I thought maybe it's my accent that thing is not picking up, but anyway, it was a microphone, I guess. I'm like, oh, it picks up the German accent, but not my accent. So.
It's doing auto translation, yeah.
Okay, so I think the point was there, are we going to use the same port or not? I mean, I think these are the type of stuff that I'm...
Because you want PIM Lite to be on the other side versus full-blown.
Exactly. PIM Lite only talks to PIM Lite. Yeah.
Stick?
Yeah. So you have this bullet point about the source DR and RP having to be on the same side, or I should say in the same domain. But I think it should be fine to have PIM Lite sitting between the first step and the RP if you want to. There's nothing preventing that.
Well, that was the register message that I thought would prevent that, no?
Oh, the register is just unicast, right? So that would just, that would just be based on unicast routing, whatever.
Okay, so just to make sure, again, I don't have the draft in front of me. The register doesn't need hello or anything like that?
No.
Oh, okay, gotcha. All right, thank you. I'll correct it.
Yeah, I mean, I'll certainly try to continue pushing for at least a should, that an implementation of this should support 6559, right? Because I just think then if we're deploying this together with beer, that would be the recommended reliability that we get, right? And I'm not sure how we actually call it. If there is a beer domain in between it, that's also, multi-access, right? I mean, the point is just we're not going to have an assert issue because we're explicitly only getting the traffic from the upstream router, right? So I think that's the right text you need to figure out somehow. It's not kind of LAN or so multi-access, right? But yeah, ping
you're absolutely right. I put my foot in the mouth when I say it's only point-to-point, and the reason I was dancing around that was because of the beer, because I know that's going to be like a point-to-multipoint kind of thing. But it's one direction. It's not both direction. But you're right. I got to get that text.
So we can't use it on networks where we would have assert issues.
Yes.
Duplicate. So that's,
exactly. Maybe that's a good
write
sentence.
in the negative and then put the positive example out. Beer domains will work. Something like that.
Yeah, got it. Yeah, that's a good way of putting it. Yeah, thanks. Anything else? Okay, I think this was good. We got some good comments out of it, so I'll go update it, and then next IETF we can have a look at it. Perfect. Thank you very much, guys. Appreciate it.
Not come VR. Or is it the MFR first? Yeah, okay.
You there, Ito?
Hi, Mike. Can you hear me? Yeah.
Yes, we hear you.
Okay. Thank you. Good afternoon, everyone. Today I will present the PIM-MFR based on the TRFA. Next slide, please. Firstly, I will give a very quick overview of this document. As we know, the PIM-MFR is a local protection mechanism that is very important for the multicast deployments. And but in the original RFC 7431, it can only use the RFA algorithm and only cover part of the network of topologies. And the TRFA for the unicast when the SR show up, and the TRFA can achieve almost 100% network topology coverage. And in this document, we provide a new mechanism based on the TRFA for PIM-MFR, and with no additional extension of the PIM protocol. Next slide, please. Here is the mechanism of the PIM-MFR based on the TRFA. For the TRFA, we can get SR repair list, including node seed and adjacent seed. For the node seed, we can use the RPIF vector attribute, the type 0, defined in the RFC 54 and 96. So the we can use the address of the corresponding node seed as the to look up the unicast routing to the node, and we can check the RPF incoming phase and upstream, and send PIM join hop by hop to build to establish the backup tree. And for the adjacent seed, we can use the explicit RPF vector attribute. That means the type 4 defined in the 7891. So the adjacent seed including two address for the link. So we use the remote address of the link as the type 4 attribute to specify the upstream neighbor directly, and which can establish the backup tree. That's the brief introduction of this mechanism. Next slide, please. For the 01 version, we update for the illustration of the PIM MFR based on the TRFA. So for the PIM-v4, we based on the SR MPRS TRFA. So in the SR MPRS, we can get the SR repair list based on the node seed label and the adjacent seed label. So for the node seed label, we can get the address of the node corresponding to the node seed. And for the like in the picture that we get the 4.4.4.4 as the type 0 attribute. And for the adjacent seed, the label, we can get the remote address of the link from the IGP. Like in the picture, we get 14.0.0.1. So we can use these two types of the attribute to establish the PIM-v4 backup tree. And for the PIM-v6 MFR, we can based on the SRv6 TRFA. For the SRv6 TRFA, we can get the repair list for the AND seed and the AND.x seed. For the AND seed, and because it's a rootable address, and we can directly use the the seed as the type 0 attribute, and we can also use another address of the node corresponding to the AND seed as the type 0 attribute. And for the AND.seed, we must get the link also get the link remote address from the IGP as the type 4 attribute to establish the backup tree. So that's the two scenario of the PIM-FOIR based on the TRFA illustrations. Next slide, please. This document will welcome more questions and comments. And for the co-authors, we think this document is stable now, and we want to ask the working group last call. That's all. Thank you.
Torles, are you in the line or no? Or Homan? Yeah.
So I think this is a great idea. I just had one question. I thought that when it comes to the TI-LFA, you don't always terminate on the next router. So you could have like a next hop kind of thing, like multiple hops away. So like in that case, what's going to happen? Are we going to create like a PIM adjacency from the router that is doing the, I guess, the recovery to the router that is multiple hop away, or again, like if you go back to your picture is two routers side by side, which I think that case will work nicely because you already have all those PIM adjacency between R2 and R6. I think that's going to be fine. But like, what if your TI-LFA, if there's R7 before the receiver, there's like another router right before the receiver, and your TI-LFA takes you to that, let's call it R7, it's going to take you to the R7. In that case, what happens? I was trying to figure it out in the draft. I couldn't figure it out, so maybe just one area to kind of clarify.
You mean what is the position of the R7?
Sorry, so the R7, imagine it between R6 and the receiver. So between R6 and the receiver, there is another router, and just imagine that your P and Q space, rather than terminating on the R6, somehow takes you to the R7, which is like 2 hops away from R2, and you don't have like a PIM adjacency between R2 and the R7. So that's my question. How are you going to create a brand new PIM adjacency between R2 and R7? And if so, wouldn't that take like a long time to do? I don't know. Am I making sense here, or am I completely offline?
We'll consider after the meeting.
Yeah, too bad you're not here. I could have pointed at the stuff. I don't know. Maybe we can take it to the working group discussion. Okay. Yeah. Just imagine that your P and Q. My only point is that imagine that your Q and P space doesn't terminate on a router that is directly connected to your R2. Imagine that your Q and P space terminates on a router that is multiple hop away from the R2. So in that case, how are you going to create the PIM adjacency and everything?
If we have multiple hops, we can use the multiple attributes to establish the backup tree. So we can
you don't need like PIM hellos between there, then, like between R2 and a router that is multiple hops away.
No. In this network, every router we in the PIM-FIR based on the TRFA, we assume that a router has the PIM neighbors. So if we specify the attribute, we look up the RPF according to the attribute. So if we don't specify, we just check the unicast routing to the next attribute, to the next RPF vector and attribute. If we use the established explicit RPF vector, we just send the a neighbor directly. If you use the type 0, that means the RPF vector attribute. We just check the unicast routing.
Okay, I think we can take it to the working group. Yeah, I was just wondering. Thanks, Annie.
Okay, thank you.
Mankamna from Cisco. So just a quick comment on his question. Actually, join is not going to go by tunnel. It is still going to go hop by hop. The only RPF vector is going to help that where to go. That is only deciding where to go, but it is still going to go hop by hop. There won't be any tunnel where PIM neighborship is needed.
Thank you.
So, so yeah, we should consider working group last call. How many people have read this? Yeah, I guess we need to do a poll. Curious how many people have read this draft, but does anyone have any concerns about going for working group last call? Anyone thinking that this is not ready for last call at this point? Or that it's not worth doing a last call? Okay, I think we'll just take it to the mailing list, and if there's no objections, then we'll start our last call. And yeah, if you have any concerns, please speak up during the working group last call, of course. Okay.
Thank you.
Thank you.
Okay, thank you. Thank you.
Good afternoon. We can go to the next slide. So we have been talking about this draft for I think quite some time, and I just wanted to give what is the scope or what exactly we are going to cover in this draft. So there are two points which is going to be covered in this draft. One is how exactly we are going to define backup DR, and why backup DR is coming into the picture right now. To me, it looks like maybe 20 years back when we defined PIM. That time convergence convergence requirement were not very restricted or very strict convergence requirement. But right now there are applications which really want to have a faster convergence in case of any kind of failure. So that is one part of the document. Second part of document talks about when you have a failure and you move to new DR, what will happen if old DR comes back, which has a higher priority. So there are use cases or there are deployments where customer really wants that once you have elected someone as DR, no matter who is coming in the network, let it be the DR. We don't want any movement across the network in the last hop router. So that is a two-part this draft covers. We can go to the next slide. So I'm not going to really talk very long for these problem statement. I think problem statement is well known that if we have R8 and R9 here on the LAN, if R8 was the DR which failed, we will not receive the traffic unless the DR re-election happens. And DR re-election is based on that how fast R9 can really detect the failure, then rebuild the tree. So there are multiple factors which will decide on how fast we can converge. Next slide. And having backup DR definitely does help in some of the scenarios where you may end up even doing live kind of scenario where both of the DRs are receiving the traffic. And since maybe the application is so sensitive to the traffic that you really don't want to lose any packet, in that case, you're okay to burn some extra bandwidth where you get traffic from the both of the side, and just last hop router decides who is going to be forwarding on the LAN. So in this case, when you have any failure on the actual DR, backup DR, as soon as it detects, all it needs is to open the gate towards access network and start forwarding. So that is where we really want to have a backup DR. Can we go to the next? Okay, so just previous slide, one more line. So one of the procedure this draft talks about is how exactly we are going to have backup DR elected. And I think we really don't need a new protocol extension for that, because all the procedures, what you are doing to elect actual DR, if you rerun the same algorithm and pick the second best DR, that becomes a backup DR for that network. And that's exactly this draft talks about, that we can still use our existing all the PIM protocol procedures, where you rerun the algorithm. If you are the second best DR, you are the backup DR. We can go to the next. And second part of draft which talks about is that having a sticky DR. So question comes that why may even we need a sticky DR? So in this LAN, if we have 4 routers and with different priorities, right now router 4 is being elected as a DR. Next. Yeah, next. When router 4 fails, our backup DR is going to take over, which is router 3 in this case. Maybe if we are using live kind of scenarios, everything is working fine. Everything is going perfectly fine. Convergence was much faster than the earlier or the base PIM RFC. Go to the next. Now the question comes, what will happen when router 4 comes back again? And as soon as router 4 comes back, it is going to announce its priority as a 400. Router 3 was DR at that time, maybe 2 was elected as a backup DR. Now 4 came, which is supposed to take over as new DR. As soon as 4 announces its priority, now 3 has to give up the DR role. 4 has to rebuild the tree, 4 has to rebuild all the forwarding state. So depending on what kind of platform, what kind of ASIC capabilities you have, you may have some traffic delay here or traffic loss. And this is what many customers are trying to avoid, that if new router is coming, we really don't want to give up on the DR role. This is the genuine case. What about if there is some false PIM message comes on the LAN with higher DR priority, and you ended up giving your DR role thinking that there is some other PIM router in the network, and we may go into a situation where we are not forwarding at all. And that is where this new procedure is coming into the picture. Next. So new procedures, what we are trying to do is still trying to keep it as simple as possible, not very much heavyweight protocol extensions here. It is the initial DR election remains as is. So network comes up, we do the DR election based on our DR priority. Once we have elected, next slide. So once we have elected the DR in the network, now we want to make sure that no matter what happens in the network, we will never give up the DR role. And that is where this new extension is coming, that can we reserve the last portion of DR priority, maybe 10 or 15, which we will use as a mutex, where once you are DR, you hold on to that max priority and you get that max priority get assigned. And now you will start announcing that as your priority. So what will happen in that case, no matter which router is coming and going, or whether it is accidental config or maybe some genuine attack, you are not going to give the DR priority role. Next. I think this we already covered. And same thing is with assert matrix, because this DR and assert, they are the one who really defines that who is going to be forwarding into the LAN. So whoever becomes the DR at once, and if we want to have this sticky behavior being there, so we adjust both of these matrix to max, so that the router which is DR will never give up. Next. So implementation, we already have implementation for sticky DR behavior, and I think similar mechanism. There are some other vendors which who they said that they are also kind of considering to implement the same behavior of sticky DR. Next.
Dino.
This is Dino. In terms of the backup DR, did you spec, sorry, I didn't read the draft. So did you spec that the backup DR should collect IGMP reports, so when it gets the role, it knows there's an outgoing interface?
Yes, it will. So And that
Because
is,
if he's elected backup DR and hasn't heard any IGMP reports, he thinks there's no members on the LAN.
yes, so if there is an IGMP report coming, all of the routers on
Oh,
the
that's
LAN
the
must
way
be
it's
getting.
implemented today. Okay, great. That's better.
I'm Loredana, Future Web Technologies. So I didn't read the draft either, but I just noticed that there's no draft.
Mhm.
Right? It's expired.
Oh, I thought I
So
submitted.
all this new stuff is not anywhere. So
Okay.
it's okay to not read stuff.
I somehow thought I did publish. Maybe I missed it.
Right. So the question I really have, I guess changing my hat to routing AD, is what about the other draft? And what are we going to do? Are we going to do two? Are we going to do one? This one doesn't say anything about the other one. The other one says that if you fail to send the hello option stuff, then you fall back to maybe this or the 7761 process. Do we really need two? What?
Yeah, no, I agree. So we need some analysis, right, to determine, do we need two different solutions, for which use cases do they solve, or is one solution enough, and which one should it be, right?
Right, and it looked, because I just went to read this draft and couldn't find it, but found the other one, and the other one says basically that because this one doesn't have the sticky, the old version, then that's why you would use the other solution. But now that there's the stickiness here, then
So last meeting, if I remember correctly, we wanted to kind of have a discussion, and if there is any technical issues with either of the draft, or the way I would look at it, it's not just because of I'm presenting this, is which one will be simpler for others as well to adopt and implement and use it.
right, so that's why I'm trying to sort of force someone to say something. And you say that there are implementations. I'm not sure about the other draft. There are implementations. Maybe there are. So I mean, there's a lot of things that the working needs to consider. And we've been working on this for the last 25 years, right? So we need to do something about it.
Yeah, and we've allocated 5 minutes for this, and we've already gone over 10. So we kind of need to move on and discuss this on the list. We very well may have two drafts that proceed. We don't know, but go ahead, Sandy, real quick.
Okay, Sandy Zhang, ZTE. The other draft from PIM DR improvement, because this improvement, this draft has been implemented and deployed. So we'd like to know if both solutions can be okay for working group or something else, right? I'm okay for the working group decision, yeah.
Yeah, I just want to say, in order to decide, we really need to understand how do they work technically, and are there issues with either of them, or to make a decision, it should be based on which solution actually works best, or solve the use cases we have. Sure. So it'd be great if the authors could work together and try to come up with some reasons why they think one draft works better than the other, and so on. Okay, thank you.
Hi, I'm Dino. Ooh. Oh, so mute the speaker until we need it. Yeah, right. Okay. So the last PIM working group in London, we were talking about group allocation mechanisms for NAT's marine ship type use case. And we decided, we asked the working group if we should do kind of a more generalized protocol. So I went off and thought about it, and Mike helped me quite a bit with this stuff. So we're going to present this new protocol. This is the first time we're presenting it at IETF, called GAP. Next slide. So what is it? It's a totally decentralized multicast group allocation protocol. And the reason I say totally is nobody else is involved in allocating the groups than the receivers and sources that are participating in the application, okay? There's no central entity that allocates the group addresses. And group addresses are allocated and are guaranteed to be unique among the GAP speakers. And the GAP nodes have absolutely zero configuration. This is where the design of the protocol will not be compromised. We want to make it totally decentralized. Next slide. So the protocol will allocate either or both IPv4 or IPv6 group addresses. The group addresses are allocated. They won't collide at layer 2. So we're trying to create unique group addresses. So if you're running over layer 2 switches, you won't have the many-to-one address collision at the MAC level. It works on a single subnet as well as a layer 2 infrastructure. If the layer 3 infrastructure. If the layer 3 infrastructure doesn't support native multicast, it will work over overlays that can support multicast. Okay. It can coexist with other group allocation protocols because we'll use a IANA gap range that doesn't conflict with those other allocation protocols. Okay, when native multicast is not available, multicast overlays will be used. Next. So how does it work? Multicast source and receiver nodes participate in the GAP protocol. There's an application-specific group name. This is the key to the protocol. The group name will always map to a unique group address. And when a bunch of applications, say one audio group or another video group, want to be able to rendezvous and join and receive with multi-sources, that they'll all use the same group name, and therefore they're guaranteed to use the same group address at the network layer. The group address is a hash of the group name. GAP nodes will send claim messages to a well-known IANA allocated GAP group to make sure that there's no collisions in the addresses. The claim message contains the group name, the group address, and a timestamp of when the group address was created by the first either sender or receiver. Next. So claim messages are sent every 1 minute. If a node is part of a group name that receives a claim message for a group name, it resets the 1 minute timer. So if there's 1,000 members in the group, there's only one claim message that is sent for the group, not 1,000 or a subset of. If a node is part of a group name and receives a claim message for a group, it will suppress its periodic table, and that's how we are able to minimize the messaging on the network. If a node uses a group address found in a claim for a different group name, that is defined as a collision. So if you have foo and you have bar and they happen to hash, it's a very rare occasion. If they both hash the same group address, we have a collision and we have to resolve the collision. Okay. Nodes that detect a collision set a 1 second random delay timer so somebody can trigger to tell the guy that he collided. So everybody else that noticed that there was a collision would back off. The random delay timer allows the first guy where the timer expires to send it, just like IGMP works, and so everybody else suppresses it. So if somebody collides, you don't have n-1 messages being sent, you only have a single message. And that's why the other nodes with the same group address suppress sending triggered claims. Nodes part of the collided group address will rehash. So what happens if you have two group names, foo and bar, and they both SHA-256 collides to the same group address? The guy who has the timestamp, who's the first creator, gets to keep the group, and the other guy has to rehash. And the hash is the group name +1, the ASCII string of group +1. And we'll do that up to 4 times if there's a case where there's more than 4 collisions for the same group. Okay, next. So what happens if the network partitions and the claim messages can't go everywhere? And in both partitions, we have a group name A and a group name B, and they both hash to the same group, and they're working just fine, and now the partition is repaired. What will happen? Well, what happens is as soon as a claim message is sent by any one of the nodes, it'll be detected as a collision, and then they'll correct the collision. Now, the way we're planning on doing it is building the protocol in the API. So when applications see that the group address has changed for them because of a collision, they know that they'll have to receivers will have to leave the old group and join the new group, and sources will have to send to the new group.
There's a question or comment. Do you want to take it now, or?
How about if I take it right before the demo?
Okay.
Okay. I think I'm almost done. Okay, next. Protocol scale, like I said, there was only one claim per group, regardless of the number of nodes using the group name. And there's at most one claim per collided group. Collided addresses are not used and converge quickly since collision detector triggers the claim. Next. Security, the way so I built an implementation of the protocol myself, and I decided to use the cipher, Cha-Cha-20 cipher. So all messages are encrypted on the network, so somebody can't inject. I mean, if you read the protocol specification, you could take SHA-256 and hash the group name, and you know what the group address is. But we're going to try to keep all the messages encrypted if possible. And we'll use a default key will be the group name, okay? And it can run in hybrid mode, so some nodes could use plain text, other nodes could use ciphertext as well. And the protocol could actually detect bad actors, and a bad actor is defined as somebody sending too fast, sending too many claims, or actually forging some of the fields in the packet, like timestamp, okay? And by doing that, so this is a work in progress, is that we're going to try to do some rekeying if we find out there's a significant amount of bad actors. Can we go for a period of time where one or two bad actors we can just live with them and drop their packets on the input queue? I believe there's a way to do rekeying, and I'll talk about that in a second. Overlays can help suppress bad actors, because overlays that are doing head-end replication could actually do admission control on receivers. So we could actually make the network more secure by using an overlay rather than native multicast, but I don't want to say that to this group. Now, regrouping could also happen. If there's too many people that are like signal jamming the group, we could actually regroup as well by using +1, +2, or +3 of the hash. Next. So we decided to put this as part of an API. So we believe the protocol is lightweight enough where you could actually run in the application library. So the application would go ahead and import a library, the GAP library, call the GAP init to start the protocol operation, and then supply a callback function. And the callback function's there in case the group changes. The application knows that the change happened. And it's a pretty simple API. There's just 4 of them, as you see there. The application would say allocate for my group, which is the group name, and it gets returned back a group address, and it starts receiving or sending to the group as it wishes. And when it's done, it can release. And of course, the application could allocate multiple groups if that's how it's designed. Okay, next. So like I said, I did an implementation of this, and I built the GAP library in Python. And I also built an application, really simple application called Echo Sender and Echo Receiver. And we're going to demo it now. We have kind of a live demo, recorded live demo. And so basically what Echo Sender does is simply just sends this message periodically, and then the receivers will receive it that are running the ER application. We have a monitoring tool called GapShark, so you can take a look on how to debug it, and then some utilities that do various things. Okay, so before the demo, did you say somebody had a question?
Yeah, Sue Chen, question.
Yes. Hi, it's Sue from Huawei. So we actually have 2 questions. The first one is about the claim message. Will it be sent in unicast or multicast manner? So if it will be sent in multicast manner, what will be the destination address?
Yeah, it's designed right now to send it only to multicast so everybody can hear the same messages. And we're asking IANA to allocate one IPv4 group address and one IPv6 group address to send to. So that's TBD on what the actual address is.
Okay, thank you. So that will be a multicast address.
Mhm.
Okay, the second question is that we mentioned that this is a uncentralized protocol. So what will the group name be allocated? Because if you allocate it in a server, so it won't be a decentralized one.
Yeah, the group name will have to be allocated by the application, by however people rendezvous, right? If we join a Zoom meeting today, what happens? Somebody out of band sends a link and everybody gets the exact same link, otherwise they can't join the conference. So that still needs to be done, but it may not need a central directory or a web page guide sort of thing like we've seen in the past.
Okay.
So it's just, we know that this meeting we're at here is called PIM, and we decided where to meet and at what time, and that's the sort of thing that's at some point along the application stack, you have to figure out how people want to join and collectively be in groups, right? So that still has to be specified somewhere, and hopefully in a simple manner.
Okay, so we would like to listen for more details in the mailing list. So thank you for your answer. Thank you.
So when you're saying across the not only layer 2 domain, but layer 3 domains, are you expecting somebody configures PIM sparse mode with MSTP, or are you doing application level flooding across the layer 2 networks?
Yeah, that's a really good question. This runs over, GAP is a protocol that kind of is a multicast application that runs on a multicast group address. So everything that we've designed over the last 20 years could be used. What we want to use, I'm sure you have an opinion on what you would want to use, but it might be hard to run GAP per se on SSM, because then you have to specify the sources, and that's going to require some centralization.
Yeah, I would think about application layer flooding by just, all the routers in such small domains have a GAP forwarder, and think how to build that.
In the marine time thing, it's a small domain, but we want this to work. This is a generalized mechanism that we want to work wide area.
Yeah, but the question is how wide area, right? So again, I mean, I would love to avoid getting into requirements to establish something like a PIM sparse mode configuration or PIM dense mode or anything else.
The spec's not dictating what we use.
No, but I'm saying that
it's kind of throwing its arms up in the air, just saying we got to get these packets to all the application nodes.
Yeah. I think the specific GAP forwarder should be possible, and then see how you also suppress looping messages and that stuff.
So I put it in the slide, but I didn't speak about it. But maybe there's a very lightweight, like an IoT node that doesn't want to run the GAP protocol, but it could still get allocations by doing a RESTful API to some other node. That's starting to feel centralized, so I'm a little bit hesitant on wanting to go with that, but that would be able to serve your purpose.
If I find time, I'll check if that forward. I mean, in Anima, we basically did ourselves application level multicasting, just to not.
Well, I view an overlay as an application level multicaster.
No, but
even though it's doing
the whole point is still being fully decentralized.
Yeah.
You just want to have routers just be able to forward the messages, flood them if you like, but without obviously creating loops. That's all.
Yeah.
The other question. So you have application A, then a little bit later, application B comes up. There's a hash. Application B goes to its group name +1. A little bit later, application A goes
because there was a collision.
Yeah, because there was a collision. So that's an application B, right? So we're now running a hash against group name B +1, so to speak, right?
B and A are not part of the same group?
No.
Okay.
It's just a hash just a collision on the hash. So application A goes away. Now comes a new sender or receiver for B. But that one wasn't aware of the B +1.
Right.
So
it comes up, its GAP node claims B.
Yep.
And then B +1 will send a triggered within 1 second to say to go to +1. So not only do you, this algorithm not only does collision detection and fixes it, but if somebody's on an old address like -1, like you're saying, that it'll be detected as well.
But how, at that point in time, given how this application A isn't there anymore, so there's some old folks, is it based on the time? Kind of, I'm older than you, and I think it's B +1, and you're younger than me, you think it's still hashed against B?
The collision resolution between A and B happened.
No, there is no A anymore, right? So
I got to go back. Got to go back to address it. The reason A won is because it created the group first, so its timestamp was less. Okay, so
Right.
when B+1 comes up, B will resolve B+1. If A comes back to the network, then everything's okay because this is running group address that it's unique to it, and the B+1 node and the B node are running on group name +1.
Right. But once A is gone, you're saying it's
We don't go back.
right. But
Yeah.
then the winner is going to be the one who hashes B against B+1 because he is older. His allocation is older than the new guy coming.
Let's take this offline and I'll explain it. Okay, so I have two demos, and it's a recorded movie. The first one is just an app demo. It's pretty high level, but it just shows you how it works. What we have here is we have, I was running this on my laptop, and I'm using Docker as the multicast media. And the three windows on the right are 3 receivers that are going to use GR to join the group. And you can see that the group name is called PIM-2023 group. And then we have a source on top that will start, and a second source on the bottom left that we're going to start. So we're going to try. This is the first time in.
Come do it.
Huh?
Come do what you did before.
Okay. Oh, I'm thinking I'm already. Oh, you don't.
I just turned the volume down. Remember to. So whatever you got to do.
Yeah, we'll see the more people in line, but
Here, let's let them go afterwards.
A demo of the GAP protocol. The GAP protocol
stands for.
I turned it off. There.
Now that's off, and then the other one.
Let's start it back. You guys have.
And I'm about to give you a GAP protocol demo. This is the second part of this. The first part was
Everybody hear that?
demo on the GAP set of applications with no detail on protocols. Here we're going to give you a detail on the protocols. So to start off where we left from part 1, we had 3 receivers on the right-hand side and 2 sources on the left-hand side. What I'm going to do for this demo is fire up this receiver and log in the coordinates. Now it turns out that we're going to join a special group name called collision PIM-2023 group, and that's going to force a collision to happen.
It went to the next slide.
Source.
We're going to back up. It went to the protocol demo and not the application demo.
A demo of the GAP protocol.
This is the application demo.
GAP protocol stands for Group Address Allocation Protocol, and it's a way for applications to get a unique group address across the network and be able to run a group receivers and sources. I'm showing 5 nodes here. You'll see the 3 receiver nodes on the right-hand side. They're going to run an application called GAP Receiver, which they're simply going to join the group that hashes from the group name PIM-2023-group. Let me start this group up. So this guy is joined. And we're going to join receiver 2 and receiver 3. So they're just waiting for messages to come in. On the left-hand side, these 2 windows are 2 senders, individual senders that will send to the same group name. The group name is PIM-2023 group, and the sender is going to send a message, a text message, multicast anywhere, and it's going to send it to the same group address that the 3 receivers are joined for. So let's start that up, and we see that the hashed group is 224.254.10.50, and that's the same group that the 3 receivers have joined, and therefore you see them receiving the messages on the right-hand side. Every message will have a sequence number, so you see that they're individual messages and they're continuing being sent. Okay, now what I'll do is I'll also start up another sender here on the left-hand side, and we'll have it send a message called multicast everywhere. And of course, it's going to send it to the same group. The group name is PIM-2023 group, and we'll hash the same group address. So let's start that up. You see that it is hashing to the same group. And then you see the receivers on the right-hand side are can interview messages from the source that's sending anywhere, source that's sending everywhere. If we stop this source here, this signature will just create messages from the first sender. If I stop the source here, this messages will be received. Just start it here, just to show you that there's no sequence number slide. And that's basically the implementation demo. If you stay tuned for the second part, you'll be able to see what's going on under the hood in the protocol demo. Thank you. Do we have time for the second demo?
Yeah, it's quick. Yeah, do it.
Go do it? And this is the protocol demo, which kind of goes under the hood a little bit. I'm about to give you a GAP protocol.
Maybe stand in the middle.
This is the second part of the two-part series.
Stand in the
The first part was a demo on the GAP set of applications with no detail on protocols. Here we're going to give you a detail on the protocols. So to start off where we left from part one, we had 3 receivers on the right-hand side and 2 sources on the left-hand side. What I'm going to do for this demo is fire up this receiver and log protocol events. Now it turns out that we're going to join a special group named called collision PIM-2023 group, and that's going to force a collision to happen from this source over here. It's intentional so we can show collision detection on a hashed group. But let's first start up this guy, and it will be doing some gap logging. So wherever you see timestamps, these are messages coming from the gap API. And otherwise, they're messages coming from the application directly. So for this guy, he is IP address .5. You can see the messages you can see on the monitor. You see .5 sent a claim message, and this guy received it. And they claim that the PIM-MOD group name hashes to 224.254.10.50. That is correct. We stored the state and we detect that there's no collisions. We'll do the same thing here for this receiver. This receiver is .6. We'll start him up and we'll see that there's no receipt from .6. It hashed to the same group that the other node did. And so there's no collision, so everybody's doing just fine. Let's go ahead and start up the source, which will hash to the group, and we'll see that the source is .8. Let's start up the application there. And we see that .8 came in, just like the other 2 nodes. Everything's good. We see the 2 receivers running just fine. Okay. Now note that these 2 receivers are joined to PIM-MOD group, and this guy up here is joined to collision PIM-MOD group. And so this source, what we're going to do here is put logging on this source, and we're going to have it send to the collision group. And the reason we're going to do that is because it's going to start sending on a bad group name. So this is just a fictitious group that is going to hash incorrectly. Okay. And as it turns out, when you come up here, you see that it was received by 7, which is the source down here, and that they claim that it was this erroneous group 224.255.255. We said that it was an illegal hash because the hashes must be one of these 4 hashes. We tried 4 times to find a unique hash for the group. So if, for example, it was a correct hash, say the 91, but there was some other group name that hashed to the same group, then a claim would be sent back with the second one, and then in fact collided them with the third one and the 4th one, and so on. So we're thinking at this point that since this .7 node hashes to this address here, that it's really a bad actor because it didn't even try one of the 4 root points. Okay? So we immediately send a claim back, and what we do is we claim that the real hash is 91, which is the first one here, and we send that out. Now, when this guy received it, go back to where it collided. The .4 node, this guy up here, he said he's going to claim the correct address, and this guy detects a collision erroneously. Okay, he believes there's test code put in to the application to believe that 225.255.225 is the real group. So this guy thinks that .4 has collided. So what he does this time is he's going to rehash using normal code and actually hash to the same group address. And now he's a happy camper, and he goes ahead and he starts sending to the new group address, the 91. And when you see that, you come down here, you see that this receiver that's joined to this address, the correct address is starting to use the application packets. And by the way, while that's all going on, this other group is just running just fine because it's completely unaffected. Anyways, thanks for listening. That's the end of the protocol demo.
Yeah, we're getting short on time, but we have but we have two people in line. So Lenny, can you keep it brief? Just a quick question or comment. Lenny, did you have a comment or?
Yes, can you hear me now?
Yeah.
Lenny Giuliano, Juniper Networks. From my vague recollection of 20-something years ago, SD and SDR kind of did functionally something similar, where it would just randomly pick an address from a block. There's a special like SD, SDR, SDP block, or maybe it was the ad hoc block. And in the spirit of lessons learned from the past, how is this mechanism different? Did you go back and look and see how that worked, what worked well, what didn't work, and how this mechanism is different than what SDR used to do?
So it's pretty much the same mechanism, but it was done at the application layer, as you know. And it was also built not only as an address allocation system, but also as a human being rendezvous system to publish, groups and content and that sort of stuff. So this is the thing. This is kind of the revelation that we said, is that multicast was always depending on things that are above its layer, when this is really a network layer function. And how do routers in the unicast world know which way to send packets? It's because the addresses are advertised through the protocol. So we're thinking that we kind of missed this a long time ago, where we should have tried to do something like this at the network layer so it was self-contained. I mean, if I wanted to do this demo with names and not addresses, I would have to it's a ping demo. Why would I have to bring up SDR to do this? So we want to put the functionality where we think it should belong architecturally.
Ice, do you have a question, comment?
Ice, Arcus. So I had the same question as Tulis, actually, on how you distribute the claim messages, right? If you want to do the allocation. Have you thought about using BSR to distribute those claims?
BFR?
BSR.
BSR. But that depends on PIM.
No, I think you can distribute the BSR messages there.
No, what I'm trying to say is GAP is an independent protocol, and its messages should be able to be sent over MOSPF, right? And it should be able to be sent over PIM, but it shouldn't have to depend on any PIM machinery to work.
No, but BSR doesn't depend on the PIM machinery, does it? It's an application level flooding. BSR, Bootstrap router.
Oh, what's that? I thought you were talking about Bootstrap messages. PIM Bootstrap messages?
Yeah, that's what he's talking
It's called BSR.
Yeah, well, that's depending on the PIM protocol. We want GAP to depend on multicast service in the network and not have to depend on the protocol mechanisms of any one given protocol.
We'll
We'll talk it offline. Okay, sure. So I'll just wrap up, or can I wrap up? Okay. So the point about collisions is we did some simulations, and these collisions are very rare. And it turns out for IPv6, it'll never happen in your lifetime because we're going to cache to 2 to the 32 addresses because we have more address space for IPv6. And it's true that we want them to not collide at a 23-bit space because we're running over a layer 2 network. But you know, the width of the hash, the uniqueness can vary as well. So what we did is we went through 1 million groups, and we said only 2% of the time we had a collision. And on the right-hand side, you could see that the collisions, most of the collisions had with 1 collision, 500 happened with 2 collisions, and 8 happened with 3 collisions. I blew it up 10x to 10 million, and we had a 20% chance. But remember, that's actually hashing to 24 bits. And if we hash to 32 bits, these numbers go down quite a bit. So we think the collision machinery probably won't even be exercised that much, but it has to be put there in case it does. Next. I think that's it. Oh, next steps, more testing, obviously. We're going to add more security features. I'm looking at the Shamir's MPC algorithm to be able to distribute a key for rekeying, so it's completely decentralized. You guys may want to have a look at that algorithm. It's kind of ingenious. It's been around for a long time, too. And then we want to test on overlays when we don't have native multicast to see how well that works. And maybe build this RESTful API based on the stuff that I answered to Torlis. Of course, write more apps to see how it works. If anybody is interested in wanting to write some Python apps and try to use it, the code is open source, of course, so you could use it. I'd be happy to help. And maybe seek more developers to do things. Next. If you want to listen to the demo slower, you can just check it out at those QR codes. And acknowledgements goes to Nate, of course, who motivated quite a bit, and other people in the hallway. So Lenny as well. And questions, comments?
Thank you. Thank you so much. All right, you're on, Nate. But we probably only have present time for your first presentation, which is the most important.
All right. Nate Carsons from Garmin and NMEA. So this is kind of a related protocol to the GAP protocol that Dino just presented. But Mike has some kind of comparisons that go compare this with what I'm going to be talking about. But kind of a way you could look at this is there's kind of 2 documents that we have in proposal status right now, which is one is how do you allocate the multicast addresses, and then the second is how do you advertise what those addresses are for applications to figure out what address they should be using. So next slide, please. So to provide a little bit more information about where all this came from, the environment that I work with is more layer 2 networks with devices that are different capabilities. So you might have a 100 megabit sensor and a 1 gigabit sensor, and you don't want to have the stream from the gigabit sensor overwhelm the link for the 100 megabit sensor. So the way that we handle this is we put the multicast streams coming from those devices onto different addresses and then use multicast snooping in a default block mode to prevent those streams from going onto the links that can't handle them. So you can kind of see this illustrated here. This is a problem with a standard switch because standard switch will just forward everything by default, and that 100 megabit sensor gets overwhelmed. Next slide. So the answer here is to block that using a managed switch and the multicast snooping. Devices will only request the streams that they are capable of handling. So it's kind of well known and determined ahead of time that stream from the radar is going to be a gigabit stream, or that stream from that other sensor is 100 megabit, and you only, as a device, are going to request what you're capable of doing. Next slide. Okay, so as we got into further, well, how do you allocate these addresses dynamically? We ran into some problems. So this is the format of a link local IPv6 unicast address. You have the interface ID right there. That's going to become important later as we get into the address allocation. Next slide. So with the way the IPv6 multicast addresses are structured is it's kind of progressed over time. You have the first RFC 1884, which has a 112-bit group ID, and then 3306 broke that up a little bit more. And you see that there's a group ID associated with that. And then finally, when you're getting into the dynamic allocation of the IPv6 multicast address, RFC 4489 is really what works well for our environment, and that essentially any device that uses Slack to get an address will have a set of multicast addresses at its disposal that it can then use to transmit on. So that group ID or the IID right there, that 64-bit block right there, that's kind of what is specific to that interface or that address. And then the group ID is what would vary for different streams coming from that specific device. Next slide. So with the multicast address guidelines here, you've got, it specifies group IDs are kind of broken into 3 different blocks. 4.1 and 4.2, those are going to be more of the pre-allocated ones. 4.3 gets into the dynamic IPv6 multicast addresses, which is going to be in the hex 800 to FFF range. Next slide. So the problem that we ran into, though, is when you go to transmit this on Ethernet, you take the MAC address, the destination MAC address that you're using on Ethernet is going to be the first 2 octets are 3333, and the last 4 octets are the last 4 octets of the IPv6 multicast address. So if you look at that link scoped multicast address right there, you have the potential. The only thing that's part of that final MAC address is going to be the group ID, and so you have the potential for different devices with different Slack addresses then getting the same multicast group ID and transmitting on the network and essentially accidentally going around that multicast snooping mechanism that we have in place. So essentially the different nodes that can generate the different IPv6 link local addresses, different IPv6 multicast addresses, but then they end up with the same MAC address, and that's the problem. Next slide. So in developing and having the original discussion around this, it was kind of interesting in that the environment that we operate in is very different. And so I want to kind of go through and establish a baseline for what we have is. So zero configuration, most of our customers don't have an expertise on network configuration and don't really want to. No internet connection, so there's no possibility of using some sort of outside server to help coordinate all this stuff. Networks are typically single subnet, although we're seeing or we're planning for networks going to multiple subnets at some point in the future. And then what we need is we need a unique Ethernet destination address. And the reason is because the switch parts that we have don't really support source specific multicast address. So we basically have to have each multicast stream needs to have a different destination address. So looking at RFC 4541 talks about how different multicast snooping vendors are handling this, and most of them, they're only looking at the IPv6 destination address. And then we also need a mechanism that's decentralized, avoiding a single point of failure. So there is an existing solution for dynamic assignment, which is MADCAP, but that relies on a server. And then we also need to account for multiple streams coming from the same host. Next slide. So we have a proposed solution there. I posted an update last night on that, and we've already identified a couple of issues that we need to work with that. But a couple of kind of key takeaways from what's in that document is there's a proposal to update RFC 3307, section 4.3. As you recall before, there were kind of 3 different sections there, and the dynamic range was hex 80 through hex FFF, so on. Basically, we need to subdivide that into different ranges. One of those would be used for MADCAP, and then the others we could have additional protocols allocated for that, such as the protocol that we'll get into a little bit here, such as GAP. This would allow these protocols to operate in parallel without causing collisions with each other. And then going beyond that, the proposal that we have in the ZeroConf draft is to use kind of an application of MDNS to ensure that the group ID is unique. MDNS is a zero configuration technology, and it would basically be probing before the initial use and then continually monitoring. So some of the features that we saw in the GAP protocol are also features here, in that if you have kind of that network partition and coming together and that consistent kind of maintaining the viability of the network, that's a part of this as well. And then basically, as we saw with RFC 4489, the application uses the group ID to generate that link scope multicast address, and then uses the MDNS technique to ensure that that address is not being used at an Ethernet level. Next slide. So this is kind of a proposed change to that range of dynamic addresses there. So we have 80 through BFFF, that's MADCAP. That's a large chunk based off of its current allocation, which is essentially the whole range. And then we say C0 through CFF, that's going to be the MDNS-based zero configuration algorithm that's described in the document. And then D0 through FE, FFFF, all of that is for other algorithms, such as GAP. And then the other thing that we thought was important to call out here is that this table does not reflect that with IPv6, there's the solicited node multicast addresses that are using the range FF00 all the way through FFFF. And so potentially somebody who's not aware of this would configure their MADCAP server to potentially be allocating addresses that are going to collide at the Ethernet level as well. So we also feel like this is an important update to note. Next slide. So basically there's the technique that it uses in order to ensure that the group ID is unique is that it uses a PTR record, or just as a note, DNS uses PTR records to perform reverse lookups. So from an example there, if you're wanting to do a reverse lookup on your IPv6 address, that's essentially what it would look like down there. You've got your IPv6 address, and then it's kind of you take that and take each hex nibble and put it in reverse to get that PTR record. So the proposal uses a PTR record for the layer 2 address as well. So there's an example there, and you're basically doing the same thing. You take each hexadecimal nibble and you separate it with your DNS labels and have a new special use domain called eth-adder.arpa, and that's what you would then advertise out there. So then the application would use the MDNS probing algorithm to continue querying for a PTR record with the generated string for that name. So essentially what you're doing here is you're taking your RFC 4489, the link scoped dynamic multicast address, you generate that using your interface identifier and your random group ID, and then you search for that group ID using the MDNS querying. If you find somebody that's using that same Ethernet address, you would then choose a different random number and continue to do that until you get one that's not being used. If you do find one that's not being used, then you publish the eth-adder PTR record with that information instead. Next slide, please. So the contents of the PTR record is the name of the application that you have as a DNS label, and then followed by the device's host name there. So for example, on a link local address, you have the special use domain local. In this case, the host name is example. So you have example.local, that's going to be its host name. And then the application would be in front. So application.example.local. So basically we have your total PTR record is going to be your Ethernet MAC address in reverse .eth-adder, and then the contents are going to be this application.example.local. Including the application in the PTR DNAME field there is what allows you to have multiple applications on the same host. Each application would be responsible for having a different application name. And then in order to prevent this from happening every time you start the network up, there's also a requirement that the application retains the group ID value in long-term storage so that when it pops up again, it will read that out and try to use that same address. It still has to do the probing just to make sure that somebody else hasn't come along and used it in the meantime. But the idea is that after the first power cycle applications, assuming it's got a consistent set of applications on the network, they never have to do that collision detection and kind of restructuring again. Next slide. That's basically it. Questions?
Yeah, we have one. Yeah.
Sunny's on ZTE. I'm a little confused with this solution and the Dino's draft. I'd like to know if they are used to solve the same problem or they are used to solve different problems separately. Yeah.
I think largely they solve the same problem. There's kind of some differences between the two. I think with the zero conf algorithm, it's built on top of MDNS, whereas GAP is kind of a totally new protocol. GAP, I think, is out in its current form is compatible with layer 2 and layer 3, whereas with the zero conf algorithm, that's kind of relying on MDNS. They are working on making that layer 3, and I don't know the status of that. I think they probably have had some success there, but there's the follow on to this, which is once you have the address, how do you advertise that? There's a proposal for that we're going to discuss in the DNSSD working group in session 4 this afternoon. I don't think we're going to have time to get into it here, so I encourage you to come that too.
So I can understand that this solution is centralized solution because it's used MDNS, right?
It's decentralized. So you could use DNS and have a central server, but it's designed primarily for MDNS and to be decentralized.
Okay. Thank you.
This is Dino. Regarding your MDNS comment about layer 2, this is a plug for overlays. You could probably not change MDNS, run it at layer 2, and if overlays do layer 2 overlays, then it'll just work. So your stuff could work on overlays with no changes, which is goodness, I think.
Yeah.
If you want to do overlays.
Okay. All right. Thank you.
Thank you very much. So with this whole address assignment topic, we will, Stig will drive taking this to the list and we'll discuss further about adoption and all that. Lewis. Oh, yeah, we're going to skip my presentation and go to Lewis. Louise? Where's the Lewis? Is it Louise or Lewis? Okay, anyway, yeah. Yep.
So, hello everyone, I'm Luis Contreras from Telefónica. I will present on behalf of my co-author Hitoshi Asaeda from NICT this draft that, well, it's a resume of a work that we presented in the past. The idea is to support multiple stream interfaces in the IGMP MLD proxies. So next, please. Yeah, as a background, so essentially the point here that we are intending to move forward is to have the possibility of having multi-homing in the proxy, so in such a way that we can have more than one upstream interface, and then either connect it to the same kind of content or to different contents, or even to different technologies for accessing some contents. RFC 4605 does not support natively the multi-hopping situation, so this is why we intend to move forward in this respect for accomplishing different use cases that we will comment later. Next, please. So the objectives of the draft essentially is to support these multiple upstream interfaces in the proxy device. We started to work as well in a requirements draft. The requirements draft didn't progress so far. I mean, it was adopted by the working group, but didn't progress to be an RFC. So the requirements are detailed in that draft. The benefits that we do foresee in having this kind of solution is essentially flexible operation. So we can select the content either based on the subscriber or even based on the content or even based on the interface. So having flexibility at the time of selecting what content we associate with a given customer. Also to go in the direction of supporting robust reception. So we will have more than one path for retrieving the content. So we can think on robust mechanisms for protecting the reception and also thinking on further use cases that now are facing these reliability issues of having multiple replicas, for instance. And then also going in the direction of reliability of the solution itself. So having a fast way of switching from one interface to another in case of problems, if one of the paths, let's say, is experiencing issues. Next, please. So the use cases we documented in the draft that you can see on the top, a number of use cases there. The I will go one by one just simply for refreshing. So the first one was the multicast wholesale offer for residential services. So thinking on having different ISPs or content providers offering content. So in a network, we could select one or the other, or one among the multiple. Also, the second one, the multicast resiliency, as said, so we will have the multiple ways of receiving the content, so we could improve the resiliency in case there is some outage of one of the interfaces. A third one about the load balancing. So typically in the ISP networks, we have some vacancy for protecting paths, so we could leverage on that capacity for receiving traffic from different, let's say, links towards a common destination. The fourth one, the situations where there are merging of ISPs with different multicast services. So this could help us to have an easier transition in that merging. And finally, the final one was the multicast service migration. So if we need to move from one multicast service to another, so we can do step by step without, let's say, losing the service from the old service provision. So just transitioning from one to the other in a smooth way. All of them are applicable for fixed and for mobile, for sure. And apart from them, also other use cases are emerging in relationship with the robust reception of flows. So with emphasis on reliability, so having multiple replicas, this kind of solution could help as well to those other use cases. Next, please. So regarding upstream selection mechanisms, what is in the document, we were commenting on different kind of mechanisms. The first one, a static interface selection, so based either in the channel or the content or the group. So channel, the subscriber, or even using priority for the interfaces according to some policy that the network provider could define. The second one will be automatic upstream interface selection. For this, probably we will require, or probably no, we will foresee that some signaling will be required. So this is a matter of further investigation to define what could be the mechanism. And the third one will be based on SDN-like approach. So with a controller configuring the different proxy elements and having an overall view of the different proxies in the network, and then programming or configuring from the controller the proxy. Next, please. Well, further more detail on the case of the centralized control, SDN-like approach. So essentially for this, we would require that the proxy supports on the management capabilities for being a control from the controller. So this, probably this would imply some kind of extension to the models that are already defined for the proxy. And yeah, the point that the proxy could interact with the different, the controller could interact with the different proxies. So somehow we could plan in the overall network how the different contents are consumed, what are the interfaces that are activated, and so on and so far. Next, please. Regarding the interface selection for the case of the controller, well, there will be different options. Either select one interface based on a specific user, so based on the source IP of the packet or the message from the user to subscribe the content, either in the source or group to be subscribed, or whatever source for a given group or whatever, or a source for what given group. Also, precedents could be defined for these different criteria. And also we consider the definition of a default interface in case of no matching no matching happen, let's say. Next, please. So next steps. So we want to revive the draft. So this was presented a long time ago. Now we are identifying these new use cases. The former ones are also prevalent. So yeah, the idea is to revive and to keep working on this draft for accomplishing this solution. There was performed a POC and was documented in a conference publication. The reference is in the draft in the new version. So we did some validation as well in the lab. The draft itself has been refreshed with few updates. We added this reference to the POC. We added reference to the requirements that were in the previous draft, also now appear as a summary table in this draft, and so on so far. So for finishing the presentation today. So the point is to collect feedback from the working group. From our side, to work on the identifiers to-dos that are expressed in the document. These are the value of the default active interval to detecting the inactive upstream interface in order to switch from one interface to another. To explore the signaling methods that could allow to configure the upstream interface via signaling, and to address security threats that could come from potential DDoS attacks. So our next action is to provide a new version for next IETF and to discuss again. And yeah, comments are more than welcome. Thanks so much.
Okay, it's Fang Gao from Zhongguo Laboratory. And since the IGMP looping proxy normally deployed with the multicast VLAN of multicast VLAN or multicast instance of VSI, I just want to confirm, is this new function could be compatible to the multicast VLAN function and the multicast instance functions of VSI?
Well, I don't have the answer now, to be honest. So let me.
Okay.
I don't have the answer now.
Okay, we can have
Yes.
the discuss in the mail list. And another question is that the IGMP looping proxy always deployed on the layer 2 equipment like the switch. And so you have the approach of subscribed based. So the identifier for the subscribed it would be or should be the MAC address or something like the MAC address of the set-top box or the home gateway.
We are considering the IP address, the
IP address?
the IP address of the message for that.
Okay, so what it needed to update the configuration of the IP address if it change the set box or the home gateway for the IP address. The configuration of the subscribe need to update.
But what we are considering, we will have the message of joining the group. So we will have the IP address, the origin IP address from the customer.
Okay.
So the idea is to use that for selecting the customer.
Oh, I understood. And the last question is if it's the approach of subscribed based and if two subscribed connect to the same DSNAM or a T or switch, which is join the same channel, what it will induce duplicated traffic.
Yeah, this could be due maybe to different policies. I mean, this could happen if there is a policy for maybe one subscriber taking the same content, or I mean, the content with the same identifier from one provider or the other. So yeah, this could happen, but we understand that this could be due to different policies. I don't know, maybe different. I don't know, different policies that could apply. So somehow we enable that flexibility. Yeah, but could be due to policies, maybe. Maybe it could be the case that the different providers have the same identifier.
Yeah.
So in this kind of transition from one multicast service to another, so you could apply those policies identifying what kind of subscriber should consume from one provider or should consume from the other provider. So identifying is the same, but the content is not the same.
Oh.
Or the provider is not the same.
Oh, okay. I got it. Thank you.
Thank you.
Thank you. Thank you for reviving this work. And we need to move on. Torres.
Yeah, great if you can do it quickly.
Well, finally, no new technology, but some really, really old bureaucracy. Next slide. So we are in the process of trying to update the status of our core protocols, IGMP and PIM and all the other stuff. And so RFC 1112 is defining the original IP multicast service, the host stack of it. And one of the big issues that it has, it includes the standardization of IGMP version 1. And IGMP version 1 is obsolete, but we still see, implementations coming up in hosts that are implementing IGMP v1 because, hey, it's the only full internet standard. Everything else we have, v2 and v3, doesn't have that level. Even if it gets that level, we still need to retire IGMP v1. But obviously, we can't retire IP multicast. So what do we do? So the proposal in this document, the BIS, is remove IGMP version 1, that is an appendix, and then just do the minor changes that are not bringing any new functionality, but just updating the text as minimally as possible. Next slide. So I already had some time in 21 and then got sidetracked with other stuff. Remove the text in version 00, then added the references to IGMP v3 and MLD v2. Obviously now when we finally get to this would be the BIS versions of that. Then also the text to make 1112 BIS apply equally to IPv6. Right now there is no document that defines IP multicast for IPv6. This is only IPv4. Then also introduce the fact that, since we introduced SSM, this service is also called any source multicast, so that term. So that's really just, nothing new, just updating the text so that it covers the broader scope. Next slide. So this time I'm coming back with 01. I converted that into the MD format. It's on GitHub and starting also some of the administrative discussions around that. Next slide. So as far as the work that probably still needs to be done technically, the Ethernet mapping for IPv6 is in RFC 2462. That is not full standard, so I need to talk with 6man if we bump that up to full standard as well. And then IANA just sent me a long list of possible IANA text that this document would need in terms of everybody referring to 1112 would need to be bumped up to referring to 1112 BIS. And then the whole bloody discussion about the 2119 language. So there's a couple of politics. I'll go faster through this. Feel free to read up on it and get back to me. So the IETF trust would like to get copyright and so on. So kind of the bureaucracy when you're trying to update an old RFC from 30 years ago. Next slide. So I think technically interesting that 1112 BIS could and maybe hopefully should be, and I think that's one of the really only interesting technical thing we might want to discuss, an update to IPv4 and IPv6, and that is pretty much because of the definition of non-IP multicast packets that wouldn't implement 1112, but which we still don't want to be considered to be multicast packet, and that is the ones with multicast source addresses. And we had some big fun in fixing these 15 years ago. So that's one interesting technical point to also discuss with 6man and IESG whether that would be appropriate. Next slide. Right, so 8504 host stack recommendations for IPv6. So that also is a question in terms of whether we should do a paragraph, a section in 1112 BIS updating that. So I was writing down here the details of what may be missing in that respect. Again, I think that's a discussion with 6man, what they think about it, whether they would like to see that. Next slide. So then there's administrative about the author. So pretty much what we're doing here is something that has been exercised exactly in the same way with the IPv6 protocol standard RFC 8200, which also goes back multiple different versions. In our case, it would be one single update from 30 years ago to now, or 32 years.
But yeah, there are all these crazy administrative things about the trust there. Yeah, and that's pretty much it. Next slide. So this, I think, is really an important update of our base protocol inventory. And the main goal, of course, is that 1112 bis goes back to be full standard immediately, like 1112 is, and then we get rid of IGMP version 1 with it. We make it applicable to IPv6, and we also have the normative reference for the ASM term. That's pretty much it. Thank you.
Thank you.
Yeah, a couple of questions on Dino and Laura.
So Torlis, are you sending a message that switch vendors should not support IGMP v1 any longer?
Oh, yes, really? Yes, I do, yes.
You are? Okay, so it's a strong statement you're making.
Yeah, I mean,
Okay.
I think we already agreed.
And if they don't support it, good luck having them take it out of their switches, then hosts won't be able to use it, or?
No, I mean, we already have the target, the BIS of IGMPv3 and MLDV2, the BIS of those is going to be full internet standard. That's what we're trying to do, right?
That's
so
fine.
that's
I'm not
already
worried
going.
what you're proposing. I'm worried about what should be removed from the past. And it sounds like there's an effort starting to tell vendors that IGMP version 1 is going to be obsoleted.
Oh, yeah,
and
yeah.
that you should take it out of your product.
Yeah, of course.
Is that what you're trying to
Yeah,
do?
of course,
Okay.
yeah. And IGMPv2, I'm not quite sure, right? But it's certainly not going to be full standard like IGMPv3, right? So.
I'm with routing AD. So I was under the impression, and I may be wrong, that the IGMP BIS 33 whatever didn't take IGMP1 out. But I may be wrong because that's a significant change. But yeah, whatever.
No, I think
what I really want to say is this. 8200 has been a very bad experience because of the normative language, because it has no normative language. And the problem has been, as maybe everyone knows in the routing area, there have been multiple interpretations of what the RFC says. And depending on who you are and how you read the text, you and I may interpret the same text in different ways.
Right.
So it concerns me that this would not have normative language, and using 8200 as a justification, to me personally, it's a bad thing because 8200 has been a really bad experience for everyone involved up and down the stack and everywhere else. Having said that, you also have a bunch of other stuff there that you want to change, updates to other stuff, etc. I would talk to your AD, your new AD on Thursday. Don't talk to me now. Talk to Jim on Thursday and get him to start working on this now. Because even if you don't change the normative language, there's still a bunch of changes. And what we don't want is to get to the ASG and for them to say, oh, no, right? Because I agree with you. If this is already an internet standard, we should go to internet standard. And we don't want anyone, pushing back because there was a bunch of changes and a bunch of other things that are happening there. So please talk to Jim on Thursday. And get him to work on this.
So just overall answer. Yeah, I obviously, with all these discussions about what can we read out of the Bible RFC 8200 with respect to SRv6 extension headers or not, I'm full aware of that, right? I'm very sure that there is no anywhere close or similar contentious text in 1112, right? It's the IP multicast host stack, the mapping to Ethernet, right? So it's all uncontentious stuff. So I see no reason to try to change any of the text other than updating the references and adding things in terms of the terminology, applicability to v6, and if we want to, these updates to 791. So there is no benefit in changing. I mean, there is no negative text, right? Nobody is not implementing the IP multicast host stack, right? So and there is no contention of what it is. I mean, tell me single OS Dino that doesn't support IP multicast host stack, right? So that's pretty much, the existence proof and the fact that the text of 1112 is fine and we don't need to redo it with 12 IETF116-PIM-20230327-0400 language.
So,
last comment.
Okay. So I wonder what it means to say do not support IGMP v1 anymore. All IGMP v1 is two messages, the query and the report. Note that report, that data point is used in IGMP v2. So you have to be careful how you message this.
No,
right?
I mean, it's not that difficult, right? What would happen is simply that if
But
you
a vendor
look,
is going to say, if I don't need to support IGMP v1, that means I'm not going to listen to those reports anymore. I'm just going to listen
No,
to
no,
the
no.
IGMP v3.
No,
Well,
no.
I mean, I'm
Right.
just saying you need to be very careful.
Yeah, but it's
This
is what you're talking about is the backward compatibility mode, which is fully standardized in IGMP v3 and MLD v2, right? So the fallback to all the messaging there is fully included in these RFCs. You don't need
including
1112 for that.
IGMP v2.
Yes, you don't need you right. You don't need RFC 1112 for that.
Okay.
Thank you, Torles. And our apologies to Jeffrey with only having 5 minutes left, but thank you. Come on up. And our apologies to Shushang for, we're not going to have enough time. I apologize. Stig and I will take you out to dinner.
Okay, so this is an informational draft. I'm presenting on behalf of the co-authors. Next, please. It was presented last time in MBOND, but this first time presenting in this home working group, PIM. So over the time, there have been, in various scenarios, people were talking about how can we scale multicast. So this draft is about some considerations there. First of all, we have 3 dimensions to consider to scale: number of receivers, and number of flows, and size of the network. So for each of these the dimensions, there is a solution. So in terms of number of receivers, the multicast can scale to unlimited number of receivers. As long as you grow the tree, you can scale. The number of flows, the solution is use tunnels. So wherever you can use tunnel multiple trees, then there is no need to maintain per tree state. And then the size of the network is, the tunneling can happen in different part of the network using different types or different instances of the tunnels. Next slide, please.
You want to take a question or no?
Hi, this is Xue Song from Huawei. Actually, it's glad to find that these 3 scaling dimensions you have mentioned, because we have almost the same considerations in our problem statement document of MSR6, if you have noticed. So also in our document, there will be the use cases why we raise these 3 points, and for which use cases one of the scaling problem may be more severe than others. So it will be appreciated, the authors of this document, to review our document, and it will be great if we can work together on this. Thank you.
Oh, okay. I to be honest, I didn't notice that. I will read that, and then yeah. Okay.
Sure, I will send you a link. Thank you.
Thanks. So in terms of tunneling technologies, I listed all this bit here. The Lisp, it was not in the draft, but Dino pointed out, and I never got a chance to update the draft. But all these are possible technologies. Next slide, please. So to do tunneling, we need overlay signaling so that the tunnel ingress to know which flows to be put onto which tunnels. And in some cases, the tunnel ingress also need to know what are the leaves that should be on the tunnel. Next slide, please. So for overlay signaling, you could be using MLDP or PIM or IGMP or MLD, all those as the overlay signaling protocol, the same, which is the same as the protocol for the tunnel traffic. The examples are we have MLDP signaling for MLDP traffic over other tunnels. This could include MLDP over targeted sessions, and then that's for MLDP over RCP P2P or P2MP tunnels. And then you could have MLDP over beer. There is a beer working group draft on that. And then for PIM as overlay signaling, that is for IP multicast traffic over other tunnels. The examples are PIM over PIM, which is Rosen MAPM, or refer to, also you can call it the PIM MAPM. The other one is PIM over beer tunnels. There's another beer working group draft on that. Finally, you can even use IGMP or MLD for IP multicast traffic over beer. Next slide, please. And next one is using BGP or Lisp as the overlay. BGP MAPN is one example, which covers both IP VPN multicast, or you can have the MLDP as the PEC protocol. Then there is a Lisp. Again, this is not in the draft yet, but it's one of the situations. Next slide, please. And finally, when you have a large network and your tunnels need to be segmented, meaning using different types or different instances of the same type in different regions. Now, when you do tunnel segmentation, those routers sitting at the borders of the different regions, we call those as segmentation points. Those segmentation points need to maintain overlay states, in particular the PIMZ routes. Next slide, please. So now the question is, on those segmentation points, how do you scale those segmentation points? Because they need to maintain overlay state. You can scale them up or you can scale them out. One point I want to emphasize here is about scale up. The multicast forwarding states is actually not much different from unicast forwarding state. Basically, you have a route pointing to some forwarding instructions. In the unicast case, the forwarding instructions could be forwarding traffic out of some ECMP branches, for example, 10 ECMP branches. In the multicast case, it's not ECMP branches, it's replication branches. So that's the only difference. The amount of information is about the same. Now, if you can scale up unicast, then you can scale up multicast, no problem. It's just that the implementation of the router, whether in the hardware or in the software, needs to be prepared to scale it up, and be prepared to control how much you want to scale. Then scale out, you just put in more segmentation points so that some flows going through some segmentation points, some others going through some other segmentation points. Next slide, please. That's basically a summary. Different scaling dimensions and different solutions. It's all mature technologies that we can put together to make it scale. That's it.
Yeah, one more comment for the previous slide. Thank you. I think I have read through the document. I noticed that RBS is treated as beer TE, and in the beer architecture, I think it is not. It is still under discussion in beer working group whether RBS can be done based on the existing beer architecture. So I think maybe we can have more discussions on this point.
Right. I was just referring to the technology, not particularly where it is done. Yeah.
Yeah. Great. Yeah. Thank you.
Thank you, Jeff.
Yeah. All right. That's it. We're done for today. So we'll take various adoption calls and stuff to the mailing list, and also any comments you have on anything that happened today, please take it to the list.
Thank you.
Thanks.
Good job. We actually